This video will begin our discussion of derivatives in 3 space. So at the very beginning of this class, we kind of motivate the whole course talking about the derivative looking different in 3 space. It's not just the slope of a tangent line at the surface of a point. If we think about walking on a mountainside, right? And if we're walking on a mountainside and I stop, and then I talk about the steepness of this mountainside, and let's do a realistic, not just a straight hillside. You could even do a hillside, nice and plain and flat. Well, if I walk along the hillside, it's a flat plane. But if I turn, let's say it's sloping to the right, like this. If I turn to the right, I'm going downhill. If I turn to the left, I'm going uphill. But I could also even turn catty-cornered and go like at a 45-degree angle and go kind of up the hill. We see this with roads all the time, that typically we take the least steep way for our roads. And we're going to talk about that, how to find the most steep way and how that applies in a lot of ways. So right now, as things sit, we're going to talk about this and break it down how to get all these derivatives. But right now, there is no just tangent line. It's too ambiguous. We have so many different directions that we could walk. So what that means is that we have an infinite number of tangent lines. At each point, you could think about this in 3 space. You could rotate that tangent line 360 degrees around that point and get a bunch of different tangent lines. All right, so what we're going to focus on, we're going to break this down, working our way up to being able to find any slope in any direction given a point in 3 space. But the first thing that we're going to do is we're going to work on just the x direction and the y direction. All right, take a look at these pictures here. This is the slope of the surface in the x direction. Notice that this line here goes in the direction of the x-axis. What this looks like, if we were to put this, look at it at the side, and maybe put x-axis here and z-axis here, we have some kind of line that looks like that, right? The slope at that point, looking at our x and y, is steep. Now, using that same surface, and you can tell, I think it's the same picture there. This is the slope of the direction running in the y. It runs along my y direction. Now what this looks like, if I were to look at it from this direction, z and y, this is a line that's not as steep. It looks almost just as steep, like that. So it's the exact same point, but it depends on which direction I look at it. If I look at it running along the x, like the xz axis over here, it's a very steep slope. This makes sense if you look at your green surface on the page there. Going that direction, it's very steep. Now, in this other picture in the y direction, it's like along the hillside. It's not as steep. So we have 2 different derivatives that we can look at, the x direction and the y direction. This is called a partial derivative, because we're not looking at x and y. We're only going to look at just x or just y. How is it growing? How is z changing with respect to just x or just y? What this could be, you could represent this as, or think about this as like let's do area of a square or a rectangle. We have length times width. Well, I could actually now discuss, once we get there, I can talk about how does the area of a rectangle change when the length changes, or just when w changes, or together. We're going to be able to look at these surfaces since we have multiple variables, not just an x. We have to look at these functions at when do they change with each variable. Okay, so let's start talking notation, and then we'll get into how to actually calculate one of these things. Okay, this is what a partial looks like. It has this like curvy D there. It's not a Greek letter or anything like that. It's a symbol that we have created. Yes, you have to use that for partial. You cannot use the normal D. The normal D stands for normal derivative. The curvy one is our partial. Okay, so this is how this is going to work, and I'm going to give you plenty of examples. Let's write this out. This holds y constant. This is the x derivative. How we say it is the partial derivative of f with respect to x. So this holds y constant. So it gives slope of tangent line to the surface at a point in the x direction with respect to x. There's another way. X direction, and then it's with respect to x. All right, this is the same thing on the bottom, so I'm going to cheat here. You may have to pause the video and copy, or you can find a way to shorthand it yourself. This now, the partial derivative of f with respect to y holds x constant, so it gives the slope of the tangent line to the surface of the point in the y direction with respect to y. So we're going to hold a variable constant, which means we're going to think about it like a constant and take the derivative. This is going to feel weird because you're going to have to undo your habits from Calc 1. So let's see what I mean. Oh, one more thing about notation. We have a couple ways to say this. This is what I have shown you so far. This is the partial of f with respect to z. X. This next thing is the partial of z with respect to x. And then we have shorthand for this. This means the partial of f with respect to x, and this one is the partial of z with respect to x. And you can see the y is right below it. So we'll use these interchangeably. I don't think I prefer one or the other. Just depends on what I'm wanting to write down. All right, so let's talk about how to calculate these things. It's going to be very strange up front. Okay, so the first thing we need is the partial of f with respect to x. Okay, this first term. I am going to take its derivative, but I'm going to treat y to the fourth like a constant. So I do the normal derivative with my x. 3 comes down. I get 15x squared, and then that y to the fourth would just be a constant, so I don't actually do anything with it. It just stays multiplied to it. Just like I could have done this. Right? Here's the derivative, and the constants just sit on the outside, then I put them together. All right? The same thing for this next one. I take my derivative with respect to x, 6x, and then it's times y, so I'm just going to leave times y because if I times the constant, just like this argument, it stays. Okay, then I have minus x to the fourth. It's just a normal derivative. There is no y. Now this is the weird part. Y to the fifth is considered a constant, so its derivative goes to 0. The same thing with the constant. A normal constant goes to 0. It's the same thing with your partials. That is a partial derivative. We just treat the other variable like a constant. Sorry, getting some kind of alarm. Of course, right in the middle of a video. Let me turn this off. Oh my gosh. There we go. Okay, so I have that. And then I'm going to take f, and I'm going to take the derivative with respect to y. This derivative with respect to y. So I'm looking here. Now I'm going to treat the x to the third like a constant with that 5. So the 4 comes down. I multiply it by my constant, so I get a 20x to the third. Then I got y to the third. This next one, 3x squared is the constant now. Okay, if I took the derivative of 5y, the derivative with respect to y is 5. So any kind of constant times y, the derivative is that constant. So if the constant is 3x squared y, and I take the derivative, I just get the constant, which is 3x squared. This x to the fourth doesn't have a y in it, so it's considered a constant. It goes to 0. And then this next one, I get minus 5y to the fourth. This constant goes to 0. This is going to take practice because you're not used to quotations, quote, ignoring the other variable. You're not ignoring, it's a constant, but we get to almost treat it like we're ignoring it. All right, this is going to help out a lot too. Your normal derivatives that you look at and you're like, oh my gosh, that's going to be nasty. They're going to be a little better, easier to deal with. So I'm doing my partial with respect to x. This normally would be a product rule if they both had x's, but cosine y is considered a constant. If I had 5 e to the x, the derivative is 5 e to the x. Any constant times e to the x is that constant times e to the x. So if cosine y is my constant, I get e to the x, that's the derivative of e to the x, and I keep my constant. Right? E to the y here is the constant, so I keep it. The derivative of sine is cosine, so I get e to the y cosine x. Very strange. You just got to get in your head that it's a constant. All right, we're going to now do the partial of f with respect to y. So now e to the x is the constant. So I get negative e to the x sine y. All I did was take the derivative of cosine with respect to y. E to the x is considered a constant. Same thing here. I get negative e to the y, just spits the same thing out. Sine x is considered a constant, so it's just tagged on just like this. All right, it's going to take practice. Like I said, I'm going to keep saying that because my students are typically in this case like, oh my gosh, I'm breaking my brain. It may feel like that for sure. Just get the practice in. These aren't going to go away. They're going to stick around the whole semester. You're going to get used to them either now or forcefully. Okay, I have one more here. We want to find z with respect to x. One gross z there. I mean, I know they're bad. My handwriting's not the best, but okay, z to the x. So I'm treating y like a constant. Now is the part where we're going to have to use other rules. Notice that y, I have two different like things being multiplied together, and y is in both, right? But x is only in one. So we're doing x now. I get to treat y's like constant, so I keep my y to the third. And then this is a chain rule. E to the something is e to the something times the derivative of that something. Now this goes back to if I had cx, the derivative of d dx, or with respect to x, is c. So if that constant in this case is x y to the third, or constant then is y to the third, I'm left with y to the third. Same argument there, right? The constant stays. So we get a y to the third. Okay, so I could simplify that to make it a little prettier. Y to the third times y to the third. We add our exponent, so I get y to the sixth, e to the x, y to the third. All right. So that's z to the x. Now we got to do zy. Now zy, I'm going to write this product rule out. The reason I know it's a product rule is if I look at both of these, they both have y in it. So curly d. So the partial with respect to y of y to the third times ex y to the third plus I leave my y to the third and then times partial of y of ex y to the third. Okay, so zy, we start this process. The derivative of y to the third is 3y squared. I keep the ex y to the third. Nothing happened to that one. The second one, I have y to the third. And now I got to take the derivative of e to the x, y to the third. Derivative of e to the something is e to the same thing, times the derivative of the inside, which is going to be 3xy squared. I treat the x like a constant, right? We could put our terms together here, maybe to clean it up. We don't have to. On test, I typically would leave it and let my grader do it, especially if you know that your grader is okay with that. I am your grader. I am saying that. So you can leave things unsimplified if you would like. Your next professor may not like that. That is up to you if you want to do that. Now, we are going to end up doing some more derivatives with this. So getting to this point where you can actually factor things out that they have in common. For instance, they have a 3y squared e to the x y to the third times, okay, and I'm going to have 1 plus y cubed. That would be a lot easier. If I had to do another derivative, I think that's a lot simpler than the line above. But it's kind of subjective. It depends on what you would like. Again, partials are going to take time and just over and over until you get used to breaking your brain to let things be constants.